What exactly is space? Is it a container that holds the matter of the universe, or is it something with its own physical properties? Why does space deform? Can space be infinitely divided or quantized? If you were to ask physicists or philosophers about what space is, you would likely be inundated with a pile of seemingly profound and yet somewhat meaningless words. Is space an endless void serving as a backdrop for everything in the world? Does it exist to fill the gaps between objects? Or is space a substance related to fluidity, like water filling a bathtub? What is space? It doesn't seem like a very difficult question to answer, but if you try to challenge your intuition and re-examine the question, you'll find it hard to come up with a clear answer. Most people imagine space as an expansive area, like an empty warehouse. Based on this perspective, space is literally an empty void waiting to be filled. It's like searching for a parking spot. The spot in that sentence is the space as people intuitively understand it. Following this concept, even if space isn't filled, it still exists as an independent entity. If the combinations of all matter in the universe are finite, then you could always travel to a far enough place and leave everything in the universe behind. At that point, what you'd encounter is absolute emptiness and an endless world, meaning that space is an infinitely extending void. This description of space sounds logical and conforms to our everyday experience. However, we must remember the lesson that whenever we assume something is definitely correct, we should take a step back with a skeptical attitude. Can we assume that space must coexist with matter? What if space itself is just the relationships between matter? If that's the case, pure space wouldn't exist, as the concept of space without matter doesn't make sense. For instance, if you want to measure the distance between two particles, you need those two particles to begin with. Without any particles at the edge, the concept of distance ceases to exist. So, what is the place without matter? It's certainly not an empty space. This perspective is peculiar and challenges our intuition, especially when we have no concept of non-space. However, a theory being strange doesn't mean it lacks physical significance. Which interpretation of space is correct? Is space an infinitely large void waiting to be filled, or must it coexist with matter? In fact, we can be certain that neither of these explanations is true for space. Neither an immense void nor simply a relation between matter. This is because we've observed phenomena that don't support either theory. You see, when you propose a theory based on the phenomena observed so far, it can perfectly explain those current phenomena. In that case, the theory is useful. But until someone discovers a phenomenon that the current theory cannot explain, no matter how perfect or intuitive it seems, you have to discard it. So why do we say neither of these theories is correct? What phenomenon regarding space have people observed? They've found that space can warp, ripple, and expand. What does this mean? If space were just a concept, it shouldn't undergo bending or expansion like this. It's as if you can't cut it into pieces. If space is meant to measure the dimensions between objects, how can we measure the curvature and expansion of space itself? For most people, the idea of warped space is puzzling because we've always mentally portrayed space as an invisible backdrop. You might imagine space like a stage in a theater, with hardwood floors and walls. There's no force that can bend such a stage, because it's an abstract framework, not a part of the universe. Its parts comprise the universe. Unfortunately, things aren't as people imagine. To understand space with ideas as cutting edge as those in general relativity, you must treat space as something with physical attributes, rather than an abstract theater stage. You have to imagine the properties and behaviors that space possesses. Material in the universe affects space, and you can pinch it, squeeze it, warp it, and even deform it. So, space is something with physical attributes. It can ripple and bend. This implies that space isn't an enormous empty room, but more like a big, sticky substance. Generally, objects can move and navigate within this sticky substance, just as we move around in a room filled with air molecules without noticing them. However, in certain special circumstances, this viscous substance can distort, causing changes in the trajectory of objects passing through it. Apart from distortion, it can also contract and ripple, causing objects within it to undergo deformation. Comparing space to a sticky substance might not be entirely accurate, but it helps us grasp the concept. We need to understand that the space we are in right now isn't necessarily something fixed or abstract. Instead, it's a tangible entity. Perhaps at this very moment, ripples in space have passed through you. Or maybe you are being stretched in some strange direction, but you're unaware of it. In fact, only recently did scientists discover that this viscous substance has always been in motion rather than still. What can this sticky space do? It can do quite a number of peculiar things. Firstly, it can expand, meaning that objects in space, even if stationary, will move farther apart from each other. Imagine yourself sitting within a large mass of sticky substance. Suddenly, this substance starts to expand. Even if someone else is sitting across from you and neither of you moves, that sticky substance between you will cause you to drift farther apart. How do we know that space is expanding? Won't the ruler we use to measure also expand along with space? Indeed, the space between the atoms making up the ruler will also expand, causing those atoms to move apart. Suppose our ruler is made of very soft candy, then it will expand. But if we have a very hard stone with strong atomic bonds, the ruler's original length can be maintained. With such a ruler, we can observe whether space is expanding. The reason space can expand is that we have observed this phenomenon. This is how dark energy was discovered, as we know the universe once expanded and continues to do so at an astonishing rate. Besides expansion, space can also warp. This sticky space can be compressed and deformed, much like marshmallows that can be squeezed. In Einstein's theory of general relativity, this characteristic of space is the essence of gravity. Warped space gives rise to gravity. If an object has mass, the space around it will warp and deform. When space is deformed, the objects within it no longer move along their initially envisaged paths. In a piece of sticky substance bent, a baseball's path will no longer be linear. Its trajectory will curve in the direction of the sticky substance's bend. If space is severely warped by a massive object, the baseball's trajectory might even become circular, much like the moon's orbit around Earth. Strangely enough, this is something observable with the naked eye. For instance, light bends when passing through massive objects like the sun or dark matter clusters. If gravity is an interaction between massive objects and not a manifestation of space's curvature, it shouldn't affect photons, as they have zero mass. Therefore, only the theory of curved space can explain how photons' trajectories deviate. Besides expansion and warping, space can also ripple. If you can understand space's stretching and curving, you won't find the concept of ripples too far-fetched. Stretching and warping can propagate within this sticky substance that is space. This propagation is known as a gravitational wave. If space is instantly twisted, this deformation would spread outward like sound waves or ripples in a liquid, but this can only occur if space possesses some physical attributes. If space were merely an abstract concept or a void, such phenomena wouldn't arise. We know that these space oscillations are real for two reasons. First, the theory of general relativity predicts their existence, and second, we've detected their presence. Somewhere in the universe, two massive black holes gravitationally bound to each other whirl at a frantic pace, causing immense distortions in the surrounding space. These ripples, like water ripples, propagate deep into the universe. With sensitive instruments, we, located on Earth, have detected these ripples in space. You can envision these ripples as waves generated by space alternately stretching and contracting. In reality, when such a ripple passes through an area, the space in that region contracts along one direction while expanding along another. Space is a tangible entity, not just an abstract void. This notion might sound quite wild, but it stems from our actual experiences. Observational results clearly indicate that the distances between objects in space aren't measured against some hidden abstract backdrop. Rather, they depend on the properties of this sticky substance that is space. If you envision space as an entity with certain physical attributes and behaviors, perhaps we can indeed understand its warping and stretching. However, this introduces further questions. For instance, You might feel that what we used to call space should now be termed a physical adhesive or physical glue, but this viscous substance would undoubtedly be encompassed by another kind of substance. Then, the substance containing this lump of stickiness would become space again. However, based on our current observations and understanding, this container is not necessary. When we talk about curvature, this curvature isn't a deformation of this viscous substance relative to some background. It's a deformation that fundamentally alters the correlations among different regions of space. Of course, the fact that space doesn't require this container doesn't imply that the container doesn't exist. Beyond the space we're discussing, there could be a larger hyperspace, an infinite void. Does such a situation exist? We don't know. Taking this further, could there be regions in the universe without space? If space is like a mass of sticky substance, could there be areas without stickiness? Could there be regions with absolutely nothing? Currently, we cannot answer these questions. All physical laws are predicated on the existence of space. When space ceases to exist, these physical laws lose their meaning. In fact, these new insights into space are recent developments for humanity. Our understanding of space is still in its infancy, and in many ways, we remain confined by our intuitions. These intuitions were quite useful when primitive humans were busy hunting and gathering. However, the nature of space differs greatly from what we imagine. In comprehending it, we must break free from the confines of our intuitions. We can delve further. Is space flat or curved? If curved, in which direction is it curved? Once you accept the malleability of space, answering some peculiar questions becomes easier. If massive objects warp the space around them, could space have an overall curvature? In other words, could this chunk of sticky substance known as space not be flat? If you poke it, space warps and distorts, but what kind of distortion is that? Would it sink as a whole or stand straight? The answers to these questions could significantly impact our view of the universe. For instance, in a flat space, if you keep moving in one direction, you can go on indefinitely without reaching an end. But in a curved space, things get interesting. If space has a positive curvature, moving in a direction might bring you back to your starting point from the opposite direction. This is a bit like walking in a straight line on Earth and eventually ending up where you started. The concept of space curvature is difficult to grasp, as our brains aren't adept at imagining such things. Why would space have curvature? The three-dimensional space we encounter in our daily lives seems stable. What does space curvature actually mean? Now let's spend a moment pretending we're creatures living in a two-dimensional space. Our world is like a thin sheet of paper, and we can only move along two dimensions, forward and backward, left and right. Suppose our world is a strictly flat surface. That's known as flat space. If this sheet of paper were to bend for some reason, then the space would be curved. There are two ways to bend this sheet. One is to make all the curves on the paper bend in the same direction, which we call positive curvature. The other is to make the perpendicular curves on the paper bend in different directions. You can think of it as all the curves along the x-axis bending downward, while all the curves along the y-axis bend upward. Ultimately, the shape you get somewhat resembles a potato chip or a saddle. Here comes the more brain-twisting part. If space is flat everywhere, then the sheet of paper representing space can expand infinitely in all directions. But if space has positive curvature throughout, then it has only one shape, spherical. More precisely, it becomes a spherical body. This way, the space we live in becomes a closed body, much like the surface of a potato. Although curvature varies across its surface, if you keep moving in any direction, you will eventually return to your starting point. This space must be closed. So, what is the nature of the space we inhabit? Is it flat or curved? On this point, science has reached a conclusion. Space indeed appears flat, with an error of less than 0.4%. Scientists have arrived at this result through two distinct methods. The first method involves measuring the sum of the internal angles of triangles. This is something we learn in school. In a flat space, the sum of angles in a triangle is 180 degrees, but in a curved space, this sum is different from 180 degrees. Scientists employed this approach by observing the early universe and identifying 3 distant points. By studying the spatial relationships between these points, the results showed that space is flat. This is the first method. The second method is based on the origin of space curvature, namely, the energy of the universe. General relativity suggests that a specific type of energy in the universe determines the direction of space curvature. In fact, the measured energy density appears to be precisely aligned in a way that space within our observed range is not curved beyond a margin of error of 0.4%. This means that the universe we inhabit is, for practical purposes, a flat space. This might sound unremarkable at first glance, but consider it more closely. It's actually quite a remarkable coincidence. Think about it. Since the curvature of space is determined by the amount of matter and energy in the universe, even a slight increase or decrease in matter and energy could cause space to curve in a certain direction. The current matter and energy content of the universe seems to perfectly maintain a flat space within our observable range. Specifically, the energy density is about 5 hydrogen atoms per cubic meter. If it were 6 hydrogen atoms or 4 hydrogen atoms, the universe would appear differently. Even more peculiarly, space curvature can influence the motion of matter, and the amount of matter can affect the magnitude of space curvature. This sets up a positive feedback loop. In other words, if the universe had slightly more or slightly less matter in its early stages, the energy density we observe today would not precisely maintain a flat space. Instead, space would become increasingly uneven. The fact that we see space as flat now means that the universe must have been incredibly flat in its early stages, or there is another mechanism at play that maintains its flatness. This characteristic is one of the most mysterious attributes of space. Speaking of the essence of space, space curvature isn't the only challenge that confounds us. Once you accept that space might not be an infinite void but could be something infinite with physical attributes, you can raise various intriguing questions. For instance, how large is space? What shape does it have? Behind size and shape lie the quantity and distribution of space. As we mentioned earlier, since space is flat, it could extend infinitely, right? Well, this aligns with intuition, but not everything that aligns with intuition is necessarily correct. Space could be flat and unbounded, flat with boundaries, or even more bizarrely, it could be flat and self-looping. How could space have boundaries? In fact, a flat space doesn't necessarily have to be boundless. Think of a plate we use in everyday life. Its surface is two-dimensional, yet it possesses a smooth, continuous edge. Likewise, three-dimensional space might also have boundaries based on certain geometric properties at those edges. More intriguingly, flat space could also loop back on itself. Imagine playing a video game, like Pac-Man. When the character exits from the right side of the screen, it reappears from the left side. Space could exhibit similar properties, and perhaps it's connected in a manner we're yet to understand. General relativity once predicted the existence of wormholes, through which distant places in space could be connected. Could there be a simple way for all the boundaries of space to be connected? This is still unclear. Lastly, let's talk about quantum space, akin to pixels composing a television screen. Could space be composed of discrete space units, like pixels, or is it infinitely smooth with countless points between any 2 points? Ancient scientists didn't conceive of air as being made up of tiny discrete molecules. After all, air appears continuous, capable of filling any volume, and it possesses interesting physical properties like forming winds and climates. Yet, now we know everything about air. Sensations like a gentle summer breeze and the feeling of easy breathing are the result of the collective movement of billions of air molecules. These properties aren't inherent attributes of individual air molecules. The same might apply to space. The theory of smooth space might seem more plausible, given our ease of movement through space. It's fluid and continuous. Nobody moves like a character in a video game, jumping from one pixel to another, right? However, can we be certain? Given our current understanding of the universe, an infinitely smooth cosmos is actually more surprising. This is because we now know that, apart from space, everything can be quantized, and quantum physics posits a minimum quantized scale, approximately 10 to the power of minus 35 meters, known as the Planck length. From a quantum mechanics perspective, space could also be quantized. Yet, as mentioned before, we aren't sure if this is the case. If space is quantized, then when we move within space, we're essentially moving from one tiny unit area to another. In other words, space could be envisioned as a grid of interconnected nodes, much like a network of subway stations forming a transportation system. Each node represents a location, and the connections between nodes symbolize the relationships between these places. This viewpoint is distinct from considering space merely as a representation of the relationships between matter, as these nodes of space could exist independently even without matter. This becomes intriguing because these nodes of space could exist independently, and they could simply be there. In this scenario, what we refer to as space is essentially the relationships between these nodes, and all the particles in the universe are essentially properties of space, rather than elements composing space. For instance, all matter could be vibration patterns of these space nodes. This might sound a bit absurd, but it's not unfounded. Our current particle theories are also based on ubiquitous quantum fields within space. What's a field? It's a value or quantity associated with different points in space. In particle theory, particles are excited states of fields. The theories and viewpoints we've discussed about quantizing space are quite similar. Physicists are intrigued by these imaginative ideas. It's fascinating how even fundamental concepts like space can turn out to be more profound than initially thought. Some even speculate that the relationships between nodes might stem from the quantum entanglement of particles, but this remains pure speculation for now. In this section, let me summarize the ongoing mysteries surrounding space. These include: first, while space is a tangible entity, what exactly is it? Second, is the space we're aware of all there is? Could there exist a larger form of space beyond it? Third, could there be regions in the universe devoid of space? Fourth, why is space remarkably flat? Fifth, can space be quantized? Our ultimate question is, what is space used for? Perhaps, just like air, space can assume different states. Under extreme conditions, it might take on unforeseen forms. This is akin to how air exists in different forms: liquid, gas, solid. The appearance of space as we know, love, and occupy might just be one rare manifestation among numerous possibilities. In various corners of the cosmos, different forms of space might await our exploration and comprehension. To answer this question, we can utilize the most remarkable tools at our disposal: the properties of mass and energy that warp space. To understand what space is and what it can become, the best approach is to observe it under extreme conditions. For instance, we can study how space gets compressed and stretched by colossal celestial bodies like black holes, which exert immense gravitational forces. If we could closely observe a black hole, we could witness how space gets torn apart. Excitingly, we're now better equipped than ever to observe these extraordinary distortions in space. Previously, we couldn't detect gravitational waves coursing through the cosmos, but now we can. Recently, humanity caught a glimpse of actual black hole images, and perhaps in the not-so-distant future, we might venture near a black hole to witness it firsthand.